P partial UP. Now in my notes, I think there's no summation there, but you should understand that that's a physics formula. So really what's going on here is I'm taking the sum over the repeated indices. And that's actually how you integrate the form, is you just calculate the partial velocities and you contract them against the components of the form and just add them up. That's what all this stuff boils down to. We pretty much saw those formulas if you kind of think about the things we started class with, but it's a little bit hidden because we were working with a basis of forms, although it's a weird one. Y wedge z, z wedge x, dx wedge dy. So those actually have two tensor things in it, right? Because like dx wedge dy is dx tensor dy minus dy tensor dx. So like that's picking up on two of the things. But so if you really look at what we had, there would have been 6 things so for example, if we're talking about a 2 form, it's just this. So it's a surface, and of course there's a sum over I and j. But if these are the tensor components of the form, if it's a 2 form, there's only 6 independent ones. If supposing we're in 3 dimensions. I'm supposing that this is a surface in 3 dimensions. Well, see, that's the interesting thing, is if this is a surface in 4 dimensions, that formula still makes sense. It's just the I and j range over more. So this is already we already know how to do we can integrate a 2 form over a surface in 4 dimensions just the same. Let me see if I can do that. Yeah, we got about 10 minutes left. We started so late. Sorry about that. All right, so just to give you, what am I trying to do right now? I am trying to familiarize us with the integral of forms to appreciate what it's doing, how it works, enough so that we can build our way to hopefully at least a sketch of the proof of the generalized Stokes theorem. That's our current goal, and we're kind of meandering. Obviously the big unchecked box is, how do you define the positively oriented boundary of a K-manifold with boundary? What is a manifold with boundary, right? That's the giant issue that we have not confronted. But before we do that, an example. So probably my examples are technically using the definition that I haven't made yet. My bad. What example am I on? 3?
I think
2. Phew, goodness. All right, so let's see here. X of uv equal to, let's go with uv, u plus v, u squared plus v squared, and 3 plus v. There you go. That is a patch of a 2-dimensional manifold in R4. And then I can take, and just to keep it, to keep it behaving, we're going to say, 0 less than or equal to u comma v less than or equal to 1. That should make the integrals that will result not too onerous. All right. So we're just going to say, x of 0, 1 squared is equal to s, which is, of course, a particular surface in R4. And now let us take a two-form. Let us take a two-form, like gamma equal to, I don't know, x dy wedge dz plus t plus y dz wedge dt. I think that's enough suffering. So, listen, the coordinate system I'm giving to R4 is, what do you want? Should I put the t first or last? First, all right, so t, x, y, z. All right. So let's see here. We can either use the pullback definition, right? Or we could use my boxed in the corner definition. If we use the boxed in the corner definition, we have to drop back to tensor stuff. We actually have to think about the components. So maybe it's worthwhile to do that for just a second. But this here only has non-zero components. Gamma, let's see, so this is 1, 2, 3, 4, if I'm enumerating that way. So this has non-zero 3, 4 component, which is equal to minus the 4, 3 component, which is equal to x. And also, you've got your gamma, let's see here, 4, 1 component, which is minus your gamma 1, 4 component, which is t plus y. So I actually kind of like my my definition I gave as a grad student, which was not born of, and that was not born, I wrote that down by intuition, not because I found it in a book or something. To me, it was just the natural abstraction of the surface integral formula that we saw in Calculus 3. So I remember when my advisor saw it, he was like, what? Oh, okay. So, it works. So if we put that into practice here, what's that look like? I'm going to use my formula if that's okay. We've done a lot of pullbacks already, so let's use my formula. So what we're supposed to do is integrate over, the unit square, and I'm supposed to take x, right? And I'm supposed to take x, and I'm supposed to evaluate it at x of uv, so to speak. Okay. Maybe I should just put what that is. What is that? It's u plus v. Right? And then, so I've got oh, goodness gracious. My bad. I need to do this I'm sorry, Ernesto. I need to let me write this down as a guide before I get lost. So I have gamma 3, 4, and then I'm supposed to do what? Partial x3, partial u, partial x4, partial v, and then plus gamma 4, 3, partial x 4, partial u, partial x what? 3, partial v, right? And then plus gamma 4, 1, partial x4, partial u, partial x1, partial v, plus, plus gamma 1, 4, partial x1, partial u, partial x4, partial v. And of course that's all integrated over du dv. All right, so this is my x1, this is my x2, this is my x3, this is my x4, right? So, and gamma 3, 4 was x, but so let's see here. So x, but x evaluated at where? X, so that's u plus v, right? And this is also u plus v, right? So we can group these two things together, right? We can group the first two terms together because we get partial x3 partial u, which is 2u, partial x4 partial v, which is 1, and then we get minus partial x4, well that's 0, and partial x3 partial v, which is 2v. See, I just, you see these guys, right? They're both this, assuming that I put the minus in because of the flippity flop of the. That minus is automatically woven into the pullback formalism with the wedge product, yeah? But anyway, so then gamma 4, 1 is t plus y. Okay, but what is t plus y? Well, t plus y is uv, y is u squared plus v squared, all right? And then I got to do my partial x4 partial u, which is 0. Partial x1 partial v, doesn't really matter, but it's u. And then again, the minus because of it's the same coefficient function. I might as well just write it once and put the minus over here. Partial x1 partial u is v. Partial x4 partial v is 1. So looks like what we're up against here is integral from 0 to 1, integral from 0 to 1 of, well, 2u squared plus 2uv minus uv squared minus u squared v minus v cubed du dv. Which of course you can finish, right? But it's probably not too far-fetched to see that the same formula is going to be created if we do what? If we just plug in the parameterization formulas for the surface, right? If we just plug in x equals to u plus v here, and if I plug in, you know, the t is uv, and the y is u squared plus v squared here, that's the pullback, and then I take the total differential of y and the total differential of z as it's defined, these guys up here, right? That's going to give me like these terms, and over here those terms with a du wedge dv, and then when we integrate that we drop the wedge, but it's the same formula. So like, you know, as a practical matter, you can use the pullback formalism to calculate these things, or you could use my handy dandy, no wedges, just straight to the formula that's actually the integral, if you prefer. I'm not sure which I prefer, but what I would prefer is next time we meet to hopefully show you some things from here maybe. This is Paul Rentland's Manifolds, Tensors, and Forms, and I'm hoping that I can crack his proof of the, I'm hoping I can explain like the orientation stuff next time, so we'll see what happens.